Uh, Hi everyone. Thank you very much for inviting me to give a talk for the Department of Mathematics at Troy University. It's very happy for me. I heard that there are some very big typhoon now is coming to Alabama also, but I hope that all of you are safe. In Vietnam, we have also a typhoon yesterday, very strong, but now it's okay. So now I will give the talk on my work, the representation of non-negative polynomials and application in solving polynomial optimization and moment problems. So I will give the motivation and the main reason in the second part. In the third part, I will give some application in polynomial optimization and solving k-moment problem. And the last part, I will give some further developments for matrix polynomials. So now I go to motivation. The first motivation of my work is on polynomial optimization. What I call the first unconstrained polynomial optimization. I denote here Rx to be the ring of polynomials in n variable with real coefficient. For in integer d, I denote Rxd, the set of polynomials in Rx of degree less than or equal to d. I denote by the sum of Rx square. This is the set of sum of square. That means the sum of square of finite polynomials in n variables. Sorry, the unconstrained polynomial optimization problem is to find the infimum f star of fx for all x in Rn. Equivalently, we find the supremum of all gamma such that fx minus gamma is non-negative on Rn. This problem is generally non-convex and NP hard. Replacing the people use the SOS relaxation. They denote FSOS. This is the supremum of on gamma such that F minus gamma is an SOS of degree less than or equal to 2D. Note that this can be computed via a semi-definite program. We call it STP, involving a matrix of side the binomial of d in n plus d, and FSOS is less than or equal to f star because each SOS is non-negative, and if it's non-negative polynomial is an SOS, then they are equal. But in general, FSOS is less than f star. For example, we consider this polynomials. This is later we call Moskine polynomials. M star equal to 0, while M SOS equal to minus infinity. So the interesting question is that when the following hold for every non-negative polynomials This is an SOS. This is I don't know by question 1. Can you hear me?
Yes, Trinh. Everything is good.
Okay. Yeah. So I continue. In this slide, I say about the constraint polynomial optimization problem. Here, for any subset G in Rx and Kg, the solution set of polynomial inequality, which called the basis closed semi-algebraic set. Notice that in the Kg equal E empty, then Kg is just Rn. And for any polynomials f of degree 2D, the constraint polynomial optimization problem is to find the infimum over Kg. That means over the basis closed semi-algebraic set Kg. I denote this by Fk star. Or equivalent, we find the subprimum of on gamma such that f minus gamma is non-negative Kg. This problem also non-convex and NP-hard. So the people consider SOS relaxation of this problem. They consider Fk SOS defined like this. Instead of consider the non-negative, they replace by this summation, where S0 and Sj are SOS. And the fact that Fk SOS is less than or equal to Fk star. And the computation of Fk SOS here does not lead yet to an SDP, because we cannot now we cannot bound the degree of the polynomials S0 and Sj. But to bound the degree of S0 and Sj, we fix integer t with this condition and denote by fkt with more t here, the subprimum of all gamma. But here we bound the degree of S0 and Sj by 2t. So we have the sequence fkt SOS. This value can be computed via an SDP, and this sequence increasing conversion to Fk SOS, but it's not converged to the optimal value Fk star here. So the question is, assume that F non-negative on Kg, when F can be represented by this summation, which coefficient S0 and Sj here are SOS. So the representation of polynomials non-negative on basis closed semi-algebraic set Kg here very important. So the reason why we consider the representation of non-negative polynomials. Another motivation I consider here the K moment problem. First, I consider k-moment problem for multi-sequences. For any closed set k in Rn, and for any multi-sequence S alpha, the question is when there exists a positive polar measure mu on k, such that we have this equality. That means the integral over k of x alpha d mu x equal to S alpha. If there exists some positive polar measure mu like this, then we can ask a k-moment sequence. For example, n equal to 1, we have this one-dimensional k-moment problem stated like this. For k equal to r, we have the hamburger moment problem. For k is this interval, we have Stirzet's moment problem. And for k is closed interval AP, we have Hausdorff moment problem. And when k is unit circle in complex plane, we have Toeplitz moment problem. The connection between moment problem and representation of polynomials non-negative on some set k by many authors, but for example, the paper of a problem to find version of some positive cylinders. For example, version of arcing theorem, theorem of Grevich's triangle, Handelman, Polya, Smutgen, Butina, or Sederer, or Schweihhofer, etc. for matrix polynomials. The second problem is to find application of these positive cylinders in control theory in optimization for matrix polynomials. The third interested problem to define some kind of k-moment problem for matrix polynomials and use the obtained positive cylinders for matrix polynomials to solve this kind of k-moment problem. I give some related reason. For example, reason on positive cylinders for matrix polynomials, the K publication of Smutgen in 2009, given the first idea to work with non-commutative polynomials, including matrix polynomials. The second is my paper in 2015, and recently my paper with my PhD student published in 2018. This gave the version of Handelman prescriptions for matrix polynomials. In this paper, I give some version of arcing, of Grevich's triangle, of Schweihhofer, or Sederer prescriptions that for matrix polynomials. So what's Schweihhofer and Sederer? I have no time to give in detail. Continue in 2006, Scherer and Hall give this publication very good in application in control theory, and in this they give the version of Butina boosted that in this paper of Zala they give a version of Smoothgen boosted that for operator polynomials and apply to solve moment problem for operator polynomials. And we have this joint work of my with Mr. Hoa and Mr. Ho from the title is some application of Scherer-Horn's theorem. Scherer-Horn theorem given here. So we apply this theorem to give some boosted generalizations for matrix polynomials. So the last part, I give some related reason on moment problem or for matrix polynomials. The first reason of Budov and Igor Klepp published in 2012 and 13. So here they propose ratio moment problem and trace optimization for non-commutative polynomials. The paper of Kim Si and Verderman published in 2013. They propose and solve truncated moment problem on RD, CD, and TD. T here is the unit circle in complex plan. So recently, I propose and solve ratio and sequential k-moment problem for matrix polynomials. This work have already accepted to publish on this journal. So that's all. I think that my time is over. Thank you very much for listening.
Yeah, thank you very much, Dr. Lei, for interesting talk. Do you have any questions to our speaker? I don't hear any question. I just want to give a short comment on the topic, like non-commutative algebraic geometry. What in 2010, I think 2012, I guess, I was looking for some problems for my research, and then there was very famous conjecture. It's called BMV conjecture in quantum information, in quantum theory, and it is formulated in the language of matrices, like trace of some polynomials, right? And then just some scalar polynomial and coefficients are trace of matrices, and they ask like trace of matrices are non-negative for any positive semi-definite matrices A and B, something like that, like A plus B T to the n. It was very famous, and that conjecture was solved after like 35 years.
Yeah.
and I think it was the very first motivation for non-commutative geometry, algebraic geometry, and until like the paper of Smoothgen on that topic, and then this topic. I think this direction is now it's very interesting. So
yeah.
Yeah, that is just and maybe I will give us some small talk somewhere next semester about BMV conjecture and some related trace inequality. But
thank you very much.
Yeah, thank you very much
for the non-competitive situation. many mathematicians have give the publication in that direction.
Yeah.
For example, Budok, Schweihhofer, Eagle. For example, what you said, BMW conjecture is have already solved, but now is the problem of non-commutative polynomials is still active now.
Yeah, it's very active,
Yeah.
and I know there are people from a big group of mathematicians from Washington University, Florida University, and University of San Luis somewhere. Yeah, they are trying to build a theory like free analysis, so free operator theory. So that is very huge right now, and I think it's very active, research topic. But yeah, it comes from here. Yeah, they have like the same motivation. All right. Yeah, thank you so much again, our speaker, for the interesting topic. Thank you.
I still have a question.
Fee, do you have questions?
Yes, I raised my hand. So I have a question. I know that in the control theory, there's a theory about positive system, which means that if the initial vector and the input are positive, then the state is always positive. And I know that there are two articles about this. This system and the relation to the positive polynomials, one by Professor Phạm Hữu Anh Ngọc in 2009, and one very recent article in the journal Positivity in 2020. So I don't know whether you are interested in linear positive system, or you have some suggestion or comments whether one can use the positive Stellensatz to study linear system in control theory.
Yeah.
Okay, thank you
very much for your question, Phi. I know that Professor Ngọc and also in Quy Nhơn University, we have also some people working on positive system, like Professor Phan Thanh Nam or Professor Đinh Công Hướng. They have already some research on positive system, and I see that there are some relation of representation of positive polynomials here and positive system. But what I see in the work of Professor Ngọc is not so much clear relation, and I try to connect to use the theory here to solve the problem of control theory. I see here, for example, the work of zero and whole now here. Can you see my screen?
Well, we still can see your screen, yes.
You can see my screen, right?
Yes.
Yeah, okay. So the paper of zero and whole here. So in this paper, they use sum of square relaxation for robust semi-definite program. I think that this idea can be for positive system, but I'm not very sure. Here they develop for sum square relaxation, but for matrices, and then they use for robust semi-definite program. And I think that we can learn the idea from here to connect to control theory. But I have not worked on this. Sorry.
Okay, thank you for the suggestion. Yes.
Yeah, thank you very much
All
for
right,
your
thank you,
question.
Phi, for your question. Do you have anything else for our speaker? So if not, please thanks the speaker again for his talk. Okay, and see you next week.
Okay, thank you very much for listening.
Yeah, thank you,
Very
everyone.
nice to see you, and see you next time.
Yeah, see you.